Every single person.
All right, let's begin. So, what do you think of the quiz? Great, good. I was having my computer repaired yesterday, so I didn't reply to many of the messages that I got. I'll do my best to give you some replies later today. Okay? Sorry for that. Now, where we left off on Monday, and we defined the notion of being regular for a vector value function. And I stated this theorem, which highlights the importance of the definition of regularity, saying that a function essentially has a coherent notion of a tangent line at a regular point. So let me remind you of what that theorem says, and then we'll discuss in great detail how to interpret it. So recall the following theorems on Monday. We had a single variable vector valued function for R to Rn, which we assume is continuously differentiable. Okay. In an open interval around some T naught, a real number. And furthermore, we'll assume that P hat is regular at T naught. What does that mean? Remind me what regular is. Yeah, exactly. It's differentiable and it's not zero at this point T naught. Good. Okay. Then what the conclusion is that there is an epsilon, positive number. Such that the image of P hat restricted, I should say, restricted to this smaller interval, T naught minus epsilon, comma T naught plus epsilon, is a smooth curve. We call C. And this non-zero derivative, P hat prime of T naught, is a vector tangent to C at this point P hat of P naught. Okay, so a lot to unpack here. Let me draw you a picture. Here's our domain, right? A copy of the real numbers. Here, I'll take my point T naught, right? And what I'm saying is that there's some open interval in which our function P hat is continuously differentiable. Yeah. Via P hat, I will come over here to Rn. Yeah. Before I draw this, what this theorem is saying is that I can find some smaller interval inside where P is continuously differentiable, right? This is P naught minus epsilon. This is bigger. P naught plus epsilon. Inside this interval, the image of P is some smooth curve. Image of P on this small interval. Okay. Really, I should put this in quotation marks. Smooth. What do I mean by smooth? This is a technical term in mathematics, but the subtleties of it are a little beyond the scope of what we're going to talk about. For our purposes, it suffices to think of smooth as just not having any sharp corners, right? Or if you prefer, the fact that at every point on this image, right, at any given point, I can draw a tangent line. And the tangent line is well defined at each point. Right? We don't have a no sharp parts. So, for example, this is not smooth. Sharp part and sharpness manifests as us not being able to come up with a coherent notion of what the tangent line is at this point. Right? If I come from this way, it looks like this. If I come from this way, it looks like this. Okay, so this is a picture of what's going on. Why do we care that we look like a smooth curve locally, that is to say, in this small neighborhood? Because everything that we've set up here allows us to write an equation for the tangent line at T naught. How did I go about this? I'm going to use the information that I assume that people here to construct an equation of the tangent line at this point. Let's say this point right here is P hat of P naught. All right, the equation of this line. Okay, so the derivative is a key component, right? That is to say, what we've said here in the conclusion of the theorem is that the derivative is a tangent vector, right? So here we just have this vector, P hat prime of T naught. But that's just a vector. We want to specify the entire line, right? All the vectors that are parallel to this. Yeah. Yeah, we'll just write the vector equation of the line using the information that we have from the theorem. Yeah. Okay, so this theorem allows us to write the vector equation of the tangent line. Sorry, I really should say at p hat t naught. Okay, so what's the vector equation of the line? What data do we need? We already pointed out that we have a parallel vector, right? The derivative of p at t naught. What else do we need to write the vector equation of the line? Yeah, a point that the line goes through. We're afforded that. Just have t naught. Okay, so L of R is equal to that t naught plus R times that prime of t naught. Here I've just changed my parameter to R because we have t as the real number equal to a function. Doesn't matter what you call your variables. Okay, great. So this is the whole initial third of the course is come up with a bunch of different ways to describe this tendency relation, right? And this is the first such instance of this, right? We're all interested in how we come up with higher dimensional analogs of tangent lines to curves. Let me present to you a somewhat perplexing example. At first, it'll seem like I'm contradicting the theorem, but with careful analysis, you'll see that things work out just fine. Okay, so let's consider the curve in R2 given by following. Well, I should really be more specific here. I should say parameterized. P hat t is equal to t squared minus 1 comma t times t squared minus 1. Okay. Let me draw you a picture of this curve. Some coordinate axes. Let's see, what do we have here? Sketch of our curve. Not exactly. Should be more symmetrical. Nice. So let me just add some annotations to this. This is how the parameterization works. Let's say here's the value of t negative 2. Value of t, say negative 1.5. At this value of t, get the negative 1. Yeah. So as we become more positive, we traverse the curve in this way. Okay. Add some more points here. is the p-value 0. Here's c is equal to 0.5. When we pass this point again, we're at 1. Let's say we have 2 up here. Okay, so what we've just shown graphically, the function is not 1-to-1 to 1, since we have the following. P of negative 1 is equal to 0, 0, of 1. Right? That is to say, there's a point in R2 that the function gets to by evaluating 2 different values of t. There's more than one t that gets us to this point. Right? So this means the image of p intersects itself. So I mean, we can see that just from the way I've drawn it, but the reason I'm saying it this way is when we're talking about parametric curves, failing to be 1-to-1 is the same as self-intersecting. So such a curve we call such a curve non-simple. Or if you like, the positive form of that definition is that a curve is simple when it does not intersect itself. Okay, so I asked you to write the equation of tangent line at this point. What was coming? Yeah, go ahead. Yeah, right. We have a non-smooth behavior here at this point, right? We have a kind of a sharp intersection. So it would appear that that this is the tangent line is not well defined at this point. However, somebody quickly compute the derivative of p hat for me. Take the derivative of the vector value function. Yeah, exactly. So you just have 2 components here. What's the derivative of t squared minus 1? Good. Three t squared minus 1, right? Okay. So we have the first thing that we notice right away is that this is defined for all values of t, right? That is to say, p is everywhere differentiable. Now, when this derivative equal to 0 vector. Yeah. Never. Yeah, why is that? Yeah, exactly. In order to make the first component 0, t has to equal 0. that gives us -1 in the second component. So we're never zero. The derivative never zero. Ah, okay. What does that mean? Yeah, right. That p is regular everywhere, right? The derivative exists everywhere, and we just convince ourselves that it's not zero anywhere. It's regular everywhere. So we should be able to write a tangent line at any point in the image of curve. What's going on here? It seems wrong, right? Yeah. Yeah, good. So that's the right intuition. How we say that in terms of what we laid out in the theorem is that we have to let epsilon be small enough. Okay, let me show you what I mean by that. Okay, so let's just record what we were saying. This implies p is regular for all values of t. Okay, so to see the image of p of t as a smooth curve around, let's say, what did I do here? T equals 1, I have to make a choice of my value of epsilon to restrict the image. Right? The entire image of the curve is non-smooth at the point 0, 0. But if I just take a smaller interval than the entire domain of all real numbers, then I can look like a smooth curve. I'm only tracing part of this curve. Okay, so what we have to do is choose small enough epsilon. Small enough epsilon. Okay, so why don't I just let epsilon be equal to 0.5 and see what happens. Okay. And let's look at p hat of t on this interval around the point t equals 1. 1 minus 0.5, 1 plus 0.5. Okay, so in other words, 0.5 to 1.5. Okay, so what does this look like? Let me make a copy of this schematic for our particular situation. R is the point equals 1. I look at this interval from 0.5 to 1.5, and I want to look at this interval under the mapping hat. This is going to take me into R2. What I draw over here, let's say 0.5 is approximately here, and 1.5 is like here. Okay. So P of 1.5, and this is P of 0.5. Right. So here we are, a smooth curve, right? We don't self-intersect here because we carefully chose epsilon. If I let epsilon be big enough so that it contains the self-intersection, then I'm not smooth. This is the heart of the theorem, that there's some small interval around each regular point where the image looks smooth. Okay. Good. All right. So all that being said, I'd like to now start talking about multivariable functions. So far, we've discussed vector value functions. Now I'd like to transition to talking about functions that take as input vectors and either give us a real number out or perhaps another vector of a different dimension. Okay, so consider a subset of Rn, B a subset of R2. Is this a familiar symbol? No. Okay. What this is saying is B a subset of RP. Likewise here. A is a subset of Rn. I know perhaps I've introduced a lot of notation, but these are like common mathematical things, right? It's good that you see them because they're everywhere in continuing mathematics. Okay. All right, so we'll take subsets of Rn and Rp, and what we'll do is study functions following form f hat going from A to B, right? Where f hat x hat equals y hat, or written out in full form if you like, f hat of x1, x2, all the way up to xn equal to y1 all the way up to y sub p. Yeah. Well, it doesn't have to be a subset, or rather, the reason we consider subsets is because we may want to consider functions that don't have the entire Rn as a domain. Likewise, for if we can be more specific about the target or the range, then we're not losing anything by moving to a subset. Right? So this is actually a more general situation than insisting that A be equal to Rn and B be equal to Rn. Okay, so oh right, sorry. We call this f a function of n variables. Into RP. Common language that we use here. Okay. Let me ask you a question. Let me look at this function of a single variable. A real output. What's the graph of this? It's of a parabolic nature, right? Okay. So when I draw this picture, what exactly am I doing? How do I construct this picture? This is second nature to us, right? We all know what x squared looks like, but what are we actually doing when we draw the graph of a function? Yeah. Yeah, I'm specifying a subset of the plane that satisfies a certain relationship. The graph, the function, they're specifying a set of points in the plane of the form x comma f of x, which since we have a formula for f of x, we might write x comma x squared. Okay. Okay. So another thing to notice here, f, our function, goes from R to R. Yeah. So when we graph a function of a single variable that has a real output, we end up in the plane, right? R2. So for a single variable, we need one extra dimension to draw the graph. With this example in mind, let's define what the graph of a multivariable function is. Okay. It generalizes to multivariable functions. In the following way. Graph of f hat is the set of points. What am I going to say? Set of points satisfying what? Yeah, just like we did here, right? We have the input, comma, the output, right? So what do we write here? X1, X2, all the way up to Xn, comma, Y1, Y2, all the way up to Y sub P. And sometimes for shorthand, we may just write this x hat comma y hat. This is very similar to the abusive notation that we encounter when we define the cross product, right? It technically doesn't make any sense to have vectors as entries in a matrix, but we do it anyway because it gives us the correct computation, right? Same deal here. We're making a vector of vectors, right? Okay. This is what a graph is. Right. Multivariable function. Function of n variables in RP. What's the dimension of this thing? Yeah. N plus p. Yeah, n plus p. In r to the n plus p. Same phenomenon here, right? F without a hat goes from r to r. The graph lives in r to the 1 plus 1. Length, r2. Good. So let's have some definitions. Firstly, let us consider a function of hat going from e to r to the p, with e, as we said before, being a subset of Rn. And let's take b an element of Rp. Then the level set of f at b, set of points at what? I'll tell you what. Set of points x hat, which are elements of E, satisfying f hat of x hat equals b hat. Okay. So in other words, we're looking for all the points of the domain that, when you plug into the function, give you the same fixed element of Rp. Okay, so let's just look back at our simple example from algebra, right? For example, in the level set of this function, x equals x squared at b, I write without a hat, right? Just because it's a single real number. Equal to 4. This level set of function. Yeah, exactly. -2 and 2. Just -2, 2. Let's come up with a graphical interpretation of this. What am I doing? I'm drawing a horizontal line at y equals 4 and determining where that intersects the graph. Or perhaps another way you might think of this is that taking a cross section of this graph. Okay, now I want to say something that is a little bit, but I think is ultimately very helpful to students in this section of the course. So as we were discussing, the graph of f sits in R2. And we know from calculus 1 that infinitesimally, at each point, this looks like a line. Tangent approximates this function very close to each point. Right? So what that means, the intuition there is that even though this is curved, the graph of this is a one-dimensional thing sitting in two dimensions, right? Because it locally looks like a line. So when we take a level set, we just get 2 points. Any finite collection of points is a zero-dimensional thing. The takeaway of all this is, as we said, the graph of a function sits in an n plus p dimensional space. Okay, and the graph itself, set of points satisfying this, is an n plus p minus 1 dimensional thing. Right? Just like the graph of x squared is a one-dimensional thing sitting in two dimensions. Right? Okay, so when you take a level set, you drop a dimension. Right? Here's this one-dimensional curve. We take a level set, we get a finite collection of points, a zero-dimensional. Try to internalize that. We're going to talk about it again. Okay. Let's continue with some more definitions. All right. So L, function from Rn to R, is linear. If and only if there is a fixed A1, A2, all the way up to AN, in Rn, so that L of x hat is equal to A1 x1 plus all the way up to AN x hat. Okay, really quick. What does this remind you of? Yeah, it's a dot product. It's a dot product of A hat, and x hat, the vector of variables. Okay. L going from Rn to R is affine linear. If and only if there is a fixed n as before, and a real number b, so that L of x hat is equal to
A1, X1, and Xn plus B.
so. These are very important terms in geometry. We will find seldom occasion to use them, but they will come up occasionally. Right, so the thing is, well, let me tell you one more definition, and then we'll talk about what those terms, linear and affine linear, actually are supposed to mean geometrically. Okay. So, for L hat, which is a function from Rn into Rp is linear, and I'll say respectively, affine linear, if and only if and only if each of its components right. So L hat has P component functions, right? It has the output has P entries, each one of those defined by some function. So we call L hat linear or affine linear if and only if each of those P component functions are also linear or affine linear, depending on which you consider. Okay. Now, what is the reason that we distinguish these two notions of linear and affine linear? Well, let's consider note level set for a linear function L of S hat at zero vector. Oh, sorry, at zero. Right? L doesn't have a hat on, so it's a scalar output. Okay, so the level set for a linear function is a line, plane, or hyperplane through the origin. Okay. So, set for affine linear function is sorry, at zero. Let's call this L naught. Zero. A line, plane, or hyperplane not through the origin. Okay, so the reason we make this distinction between linear and affine linear is because quite often in geometry, we are primarily concerned with linear structures that pass through the origin. Right? If you're curious about this, look up the projected plane on Wikipedia. Okay, but this is more of a historical note than anything. It's not exactly related to anything that I care about that much in this one, but it's just to borrow the terminology and distinguish concepts. So remember when we were discussing vector valued functions of a single variable, the familiar notions of calculus generalized in a fairly straightforward manner. You have to be a little more careful when we talk about the notions of continuity and differentiability when we allow ourselves multivariable. So, I'll give you a definition. What does it mean to be continuous? Well, let me tell you. The subset of Rn A hat, an element of E, and we'll take R hat going from E into RP, and we say R is continuous at A. If and only if for each positive number epsilon exists a positive number delta so that if x hat satisfies the magnitude of x hat minus a hat is strictly less than delta, then it must be the case that the magnitude of r of x minus r of a is strictly less than epsilon. You've seen this before. I'll tell you that this is almost word for word the definition of continuity for functions of a single variable that have a real output. The only place it differs is that we are now talking about the magnitude of these vectors, not the absolute value of the differences, which is what we talked about in functions of a single variable. So let me just add a tiny piece of this. We call R continuous if and only if R is
continuous at all points A in D. Okay, so continuity is a pointwise condition. That is to say, you're checking if something is continuous. Really, what you're doing is checking that it's continuous at all points. So, what is the spirit of this definition? What is it trying to communicate? What does it ensure? Well, what it means is that we take a point in the domain of a function and we move around a little bit around that point so that in a way that we stay in the domain. This definition is ensuring that the graph of the function doesn't change too much. A little change in the domain should translate to a correspondingly small change in the output of the function. That's kind of what this is saying. Okay. So, say, just here's some obviously non-continuous function. Okay. Discontinuity. So what we're saying here is, let's say this is our point A is f of A. So what I'm saying is we have f of A plus epsilon, f of A minus epsilon. We'll have A minus delta is A plus delta. So this is to say, for every choice of epsilon, I should be able to construct a delta so that I stay within this on the graph, right? This is not continuous. And then this is to say every choice of epsilon, any epsilon, right? That is, each positive epsilon, I can make that integral as small as I like. Later this afternoon or this evening, I'm going to send out a practice worksheet. It's not due, you don't have to turn it in, but it deals with this concept. To give you a better understanding of how to work with these epsilons and deltas. Okay. This is a very laborious definition to work with. So we're going to build a bunch of theorems about how we can check the continuity of the function without having to appeal to the definition every time. Okay. And this is going to be intuitive, like we thought of continuity before. Just always keep in mind that this machinery is what lies at the foundation. So, take our function r hat, which goes from E to RP. There again, the subset of Rn. And let me tell you a sort of formula for r hat by r hat x hat equal to, it's written in terms of its component functions, R1 of X hat, comma, R2 of X hat, all the way up to RP of X hat. Just reiterating what I was saying before, right? Since R maps into RP, it has P component functions. Then R hat is continuous. If and only if Ri is continuous. Of course, where I ranges from 1 to P. Okay, so this isn't terribly helpful, but at least we know that this notion of continuity behaves nicely with respect to the vector value function related to its components. So here's the cheat. Here's what's going to happen for most all the functions that we deal with. So, all elementary functions are the following: constants, powers, polynomials, exponentials, and so much more. Logarithms, trig functions, what else? Inverse rate functions. And furthermore, any finite combination of these using addition, multiplication, and composition. Okay, so basically, all the things that we're used to working with when we talk about functions, the elementary functions, of course, lots of other functions, right? But mainly those are pathological or constructed for a very specific purpose. Day by day, these are most all the functions that we work with. Okay. So, here's a statement that I'm sure you know. All elementary functions are continuous. Be careful here. They are continuous in their domains of definition. E.g., I take g of x equal to 1 over x.
This is continuous in its domain of definition. It's not defined at 0. There's an asymptote there. You might think, oh, this is a discontinuity. No, the function is not defined there. And it's continuous where it is defined. Okay. Okay. Good. So we'll talk a lot more about continuity tomorrow. Have a good afternoon.